So can you confirm that you can see my screen? Can someone confirm that you can see the screen?
Yeah.
Oh, okay. So, okay.
Yeah.
So this, so it says if A, B, and C are positive integers, such that the GCD of A and B is equal to 1, and A divides the product of B and C, then A must divide C. So basically this says if you have two numbers, A and B, which are relatively prime means the GCD is equal to 1. And if the first number, A, divides a multiple of B, this is BC, then A must divide C. So we proved that. Now previously we had made this statement that if we know that a GCD of two numbers A and B, two integers rather, is equal to 1, we can find another pair of integers S and T such that 1 is equal to SA plus TB. This is always possible. Using the Euclidean algorithm, this is always possible. We've seen how to do it. So multiplying both sides of this equation by C, we get C is equal to CSA plus CTB and so on. And we know that we can rearrange this so that C and B are here in brackets. And now since A divides BC, we can write BC is equal to KA. So we replace this BC with a multiple of A. And then we, at the end here, finally, we pull out the A since it's common to all the terms. And we are able to show that now A divides C because we've been able to write C as a multiple of A. So A definitely must divide C. So the fact that A does not divide B was used here. The fact that the GCD of A and B is equal to 1 was used here. Okay, so so we can write it in a little more general form. This one says that if P is a prime number and P does not divide, or rather P divides a product of n integers, A1, A2 up to AN, then P must divide at least one of these integers in the product. So one of these integers must be a multiple of P. If none of them is a multiple of P, then P cannot divide the product of this integer. So the proof was left as an exercise. Hopefully you have had time to look up the proof. So as we said here in this, there's this last part in this slide, this last statement. It says that we need to explore what happens when you divide both sides of a congruence by the same integer. So we want to explore this this idea. Let's see how it goes. So we start by an example to motivate us. Here we have an example. 14 is supposed to be congruent, not equal to. It should be congruent, so these should be 3 parallel lines. You know that 14 is congruent to 8 modulo 6. The reason for that is if you subtract 8 from 14, you will get 6, and 6 divides 6. So 14 is congruent to 8 modulo 6. So if we divide both sides by 7, so suppose we divide this by 2, sorry, divide both sides by 2, we end up with 7. But if we check, 7 minus 4 is equal to 3, but 3 is not divisible by 6. So technically, we end up with this as a conclusion. 7 is not congruent to 4 modulo 6. So this tells you that you cannot just go and it doesn't work like the usual equations where you can divide both sides by let's figure out how do we deal with this. You can hear me?
Yes.
Yes.
Okay, good. So
Not
now
clear to raise.
Yes.
Pardon?
Yes.
Okay. So this theorem will help us make this decision on how to know when we can cancel out or divide by the same constant. So let m be a positive integer and let a, b, and c be any other integers. So if this equation holds, if AC is congruent to BC modulo m, and the GCD of C and M is 1, then it's possible to divide both sides of this by C, and you'll get A is congruent to B modulo M. So that works if C and M are relatively prime. Yes, Dennis, you have a question? Dennis. Why is he raising his hand? Or maybe his microphone is off. So that is how it works. Let's prove this. So here, since AC is congruent to BC modulo M, that's the assumption we're given here. So we have to work with it. Then it means this difference, AC minus BC, must be divisible by M. That's the next statement we make. So that means M divides A minus B multiplied by C. C is common here, so we can pull it out. Now we know that GCD of C and M is equal to 1, right? And by the previous theorem, this if the GCD of M and C is 1, then M must divide A minus B. That's the previous theorem we just looked at. We saw that if A divides a product of two numbers, right? And we know that GCD of A and B is 1. This is what we have just done in the previous theorem. The GCD of A and B is 1. So if these two conditions hold, then we are left with only one option, and that is that A must divide C. So that's the same situation here. So, but what plays the role of C here is this A minus B, and C plays the role of B in this theorem. So this shows us when we can divide by the same constant on both sides. So let me get rid of these writings, then we can proceed. So we can illustrate this with an example. So for example, we have here is a congruence. We have 85 is congruent to 25 modulo. 85 minus 25 will give us by 6. So this is true. But we want to see, can we make this, can we cancel out and still get another congruence that is true? So we notice that 85 is the same as 17 times 5, and 25 is the same as 5 times 5. So 5 is and 6 are relatively prime. Since the GCD of 5 and 6 is 1, then it's possible for me to cancel out this, divide both sides by 5, and I still end up with a congruence that holds. So if 5 was not relatively prime with 6, it's 5, 12, and 12 is divisible by 6. So this is true. 17 is congruent to 5 modulo 6. So this gives you an example where we have applied that theorem, and we're able to see that it's possible to cancel. So now we, using those ideas, we can now talk about a certain type of congruence. We call them linear congruences. So a congruence of a form AX is congruent to B modulo M, where M is a positive integer. We have A and B are integers, and X is a variable. So we don't know what X is. We are looking for the value of X that satisfies this congruence, right? So we call it a variable. So such a congruence is called a linear congruence. So where we have A and B are known, M is known, but we want to find a value of X that will work for this congruence. So we shall look at some ideas on how to solve this in this section. So to begin with, we make the following, we go into the following discussion. If we have an integer, which we call by A, so we just distinguish it from A by we distinguish it from A by putting a bar on top. So this small bar will distinguish it from A. We get another integer by A, so that when multiplied by A, this integer will be congruent to 1 modulo M, and M is some positive integer. If you can find such an integer by A, then we call by A the inverse of A modulo M. Right? So this is not always possible to find. We shall see situations where we can find such integers. So for instance, if you consider if you work modulo 5, if you have 2 times 3, what it will be congruent to 1 modulo 5. Is that correct? It will be congruent to 1 modulo 5. You can see that. So because of this, now I can say 2 is the inverse of 3 modulo 1, or I can also say 3 is a modulo 5. I can also say 3 is the inverse of 2 modulo 5, because I found some number which, when multiplied by 2, this congruence is satisfied. 2 times 3 will be congruent to 1 modulo 5. Yeah. Try to put off your microphone, please. You guys are adults. Eh? I don't have to keep telling you this. So there is an example where we have the inverse. So this is not always possible. Because for instance, if I work modulo 4, if I work modulo 4, I can try to find an integer which when multiplied by 2 will be congruent to 1.
Any classic.
It may be a bit difficult to find.
I stand up.
Duncan, please, people, if you don't want to be in class, you can just get out. You don't have to make noise for us. If you have something that is more important to do, leave class and go and do it. Don't sit here and make noise for us. So let's see how we can determine when the inverse exists. So that's the next task. How do we determine when such an element exists? If I'm given an element A and I want to find its inverse modulo M, how do I know that it exists or doesn't exist? Inverse of three modulo 10. There are other numbers as well, which can work other than 7. So for me to find all other numbers that work, I just look for numbers that differ by 10, by multiples of 10 from 7, because I'm considering this modulo 10. So I can consider 7. Any other number that differs by a multiple of 10 from 7. Next one is 17, 27, and so on. So you can check what happens. If you multiply 3 by 17, you get what? You get 51, right? And 51 will still be congruent to 1 modulo 10. So any other number which is congruent to 7 modulo 10, that means any other number that differs from 7 by a multiple of 10 will still can replace 7 here, and this congruence will still hold. If you try 27 times 3, 27 times 3 will give us what? 7 times 3 will be? Alvin Mwenda, please. I'm going to kick you out of the class. So 27 times 3 times 7 will give us 21, and 3 times 2 is 6 plus 2. Is that correct? 81 is...
Yes, it is correct.
81 is still congruent to 1. So there are many different numbers that will work. Is there a question? So 81 is congruent to 1 modulo 10. And this will be true for any other number by a multiple of 10. So any number that differs from 7 by a multiple of 10 will be a number that is congruent to 7 modulo 10. And all of them will work if you replace 7 with those numbers. So there's a multiple, a very long infinite set of numbers that will work. But we can make this a little more elegant by restricting ourselves to numbers between 0 and 9, right? So if we are looking for inverses, if we focus, since we are considering this modulo 10, if we limit ourselves to numbers between 0 and 9, then only one of these numbers will be an inverse of 7, modulo 10. Then we have a unique inverse. But if you want to expand this to the larger set of integers, then any other integer that is congruent to 7 modulo 10 will be an inverse of 3. So most of the time we'll be interested in working with integers that are less than, for instance, is m. If this was modulo m, will be this as true. So we can keep doing this until we get to, we consider only integers that are strictly less than m, from 0 all the way to m minus 1. So here, if m is 10, 10 minus 1 will be 9. That is the last integer we consider. So that way we are sure that we get a unique answer. The others will be correct if you want to use them, but if we stick to this set, then we get a unique inverse for 2. So in this set, the only inverse for 3, the only inverse for the number 3, modulo 10, is 7. So you'd have to go outside this set. Now, the other thing you will notice, even the negative numbers are okay, because again, the next one, if number that differs from 7 by 10 to the left, I think, will be negative 3, right? Then you can also have minus 13. Is that correct? Yeah, I think it's minus 13. So you can check that if you multiply 3 times negative 3, you still be congruent. This is 9. So there you go, minus 3 is negative 3 is also an inverse of 3 modulo 10. Negative 13 will do the same. The reason for that is you should see that if you have minus 9, if you're considering this modulo 10, this will be the same as, I think it's this software is trying to update. So anyway, negative 9 is congruent to 1 modulo 10. So because you can write as negative 1 times 9 plus something is not right. Work this out. I want to move on to the next section. Just work it out that negative 9 is congruent to 1 modulo 10. And an easy way to do that, actually the easiest way, is to simply, if you want to check that it is true, if you have minus 9, draw. Let's go back. So an easy way to check that is if you have minus 9, if you subtract 1 from minus 9, you will get minus 10, and minus 10 is divisible by 10. So this tells us minus 9 is definitely congruent to 1 modulo 10, because the difference is divisible by 10. You can check this for all the other values. We have checked this for minus 13, so you can check it for minus 13. We'll check it for minus 3. So check it for minus 13. The next one will be minus 23. These ones will all be inverses of 3 modulo 10. But like I said, we're only going to restrict ourselves to numbers that are strictly smaller than 10, unless otherwise stated, so that we end up with a unique inverse. or if you're asking for an inverse, everyone gets the same answer if we stick to this set. So the integers that we are looking for are those that differ from 7 by a multiple of 10. So you can write them as 7 plus 10k, the inverses of 3 modulo 10. So any integer of this form will be an inverse of 3 modulo 10. So here is an example. I think we have looked at this. So I think this is okay. And when it is possible to find the inverse of an integer modulo m, it says the following: if a and m are relatively prime simply means the GCD of a and m is equal to 1. It's supposed to be a, it looks like d. Let me correct it here. If this is equal to 1, then the inverse of a modulo m exists, and it will be unique modulo m. So unique simply means any other number that differs by the inverse by a multiple of m will also work. Modulo m, that's what it means. So this is what I've just explained, and we also talked about this in the previous example. So here is a proof for that theorem to show that the inverse exists if the GCD of A and M is equal to 1. Now, again, from the previous theorem, we stated that if you get the difference 1 minus s, this will be congruent to, will be equal to a multiple of m. So, so this simply means now, this is the definition. Just a minute. This means SA is congruent because the difference is a multiple of m. It means that SA will be congruent to 1 modulo m. And since it's congruent to 1 modulo m, we have found the inverse. The inverse is just this s. And the Euclidean algorithm can help us to find s and t. And once you find s is the inverse we are looking for. So anytime the GCD of a and m is 1, it's always possible to find the inverse of a modulo m. And that would be this s here. So this gives you the exact condition under which you can find the inverse of an integer modulo m. So if the GCD of a and m is not 1, then it's not possible to find the inverse of a modulo m. So for instance, I gave you an example. If m is 4 and you want to find an integer, let's call it x, that is congruent to 1 mod 4, then you just need to check on this first set of integers. If you can't find anything in this first set, then it doesn't exist. So if you check them one by one, 2 times 0 is not congruent to 1 modulo 4. 2 times 1 is not. 2 times 2 is not congruent to 1 modulo 4. and 2 times 3 as well is not congruent to 1 modulo 4. So none of the numbers here will work, will not have a solution. And the reason it doesn't have a solution is because the GCD of 2 and 4 is not 1 actually. GCD of 2 and 4 is equal to 2. So you cannot solve this problem. You can't find x, an inverse of 2 modulo 4. It can only work if this condition is satisfied. I will stop there for today. I was again invited to be a judge for some business competition. And I think they're about to start the session. So if you allow me, I can stop here, then we can continue next week. Unless anyone has a question. Does anyone have a question? If there are no questions, we can stop there. So I think I will stop recording.